Good afternoon, ladies and gentlemen. I hope you guys are all doing well today. Welcome back. We're going to be looking at our first section of notes in our last unit, atomic physics. So please remember, ladies and gentlemen, that because we are shut down for COVID, that this last unit is optional. Okay, so as you guys are chipping away at home, enjoy the videos. I will put up an assignment shortly on Google Classroom for you guys at that. And then, intelligent. Oh, that's right. So if you guys are choosing to do this video or do this unit, awesome. I do recommend it if you guys are going to be going into a physics-based career or a science-based career. It's a very good idea to take this unit. All right. Okay. So, ladies and gentlemen, let us begin. All right. So we're starting out with a not too difficult lesson today. Nothing too crazy. Some of the stuff you will have seen before back in Science 10. We may go into a little bit more detail. We'll go into a little bit more detail with it, and then we will go from there. Okay. So, ladies and gentlemen, as I'm sure you guys remember, Dalton was the first scientist who proposed an idea of a model for the atom. He suggested that the atom is tiny, indivisible, and like an indivisible chunk of matter. Imagine like a pool ball. Okay, you can't break down a pool ball into anything smaller other than to have like broken bits. All right. So that was his first, the very first suggestion of the atom. Now, however, with the development of a cathode ray tube and the discovery of cathode rays, the model of the atom needed to be revised. Now, what a cathode ray tube is, it's a set of parallel plates or electrodes that are going to be placed in a lovely gas tube or a glass tube containing gas under low pressure. Okay. And ladies and gentlemen, if we were in class, we'd play with some of these, but sadly, we're not in class. All right. So ladies and gentlemen, when you apply a voltage across these plates, the gas in the tube is going to glow. It's actually super cool. Love playing with these things. And a cathode ray is going to be emitted. So this is what a cathode ray tube looks like. You have your cathode and you have an anode. And these here are your parallel plates. Okay, so then you got a fluorescent screen on the other side there. And then you got this beam that's going to go through this glowing gas. And that is your cathode ray. Now, why do they call it a cathode ray? Well, it's a beam coming from the cathode. Okay, I like the names and some of these scientific things. They make so much sense. They're so logical. Okay, so because Thomson did a whole bunch of work with the cathode ray tubes, he was able to observe some really cool stuff about them. So what he noticed is they traveled in straight lines. Now this is the key. This is the key, ladies and gentlemen. These things could be deflected by both magnetic and electric fields. So because of that, there cannot be EMR. These weren't just beams of light that he was seeing. And they did a whole bunch of different tests, and it didn't matter what the tube was made out of. It didn't matter the type of glass. It didn't matter if the tube was metal, a type of metal for the electrodes. It didn't matter. The properties were identical. So what that was telling him is that, well, first of all, it's not light. It's not EMR. Okay, well, therefore, it can be predicted it could be a particle. And it doesn't matter what it is, the gas or the metals, it doesn't matter. He's still getting this cathode ray. So therefore, he was able to interpret, well, maybe whatever this cathode ray is found universally. Okay, so what he did is he applied an external electric field, so more parallel plates. Okay, your guys' favorite, we're bringing back in forces and fields here, our second unit. And he would observe that the rays always bent towards the positively charged plate, which, ladies and gentlemen, as you can deduce, means it's a negatively charged particle. Okay, so here's our lovely picture. It's a really nice picture. I quite like this one. Okay, so you can see your cathode ray coming around through here. These are the parallel plates that are creating this. And then he's got these parallel plates, and the beam is curving upwards toward the positive. Obviously, negative. Okay. Where's my little bar? There it is. Okay, so ladies and gentlemen, he determined these to be tiny negative charged particles, the electron, adorable little electrons. So he then had to modify the model to be our raisin bun model or the plum pudding model. So he imagined that the electrons were like little raisins in a cinnamon bun and that they were embedded inside a positively charged sphere, like the dough of a bun. So, ladies and gentlemen, well, why would he say that it would be a positively charged sphere that these little electrons are embedded in? Because the atoms are neutral. Okay, so the model had now changed from our raisin bun model to a still component, but just one indivisible chunk in which you could kind of pluck bits off, or components, but one piece. Okay, like one piece you could pluck bits off of. Sorry guys, more technical difficulties. Now we're back. All right, so ladies and gentlemen, where we left off was talking about how the model of the raisin bun was used to explain our atom structure. Now that, so far what we've looked at shouldn't be super new to you guys. That should have been mentioned a couple years ago when you took Science 10. Now, though, we're going to add a new piece here to the material. So Thomson, he continued to work with the cathode ray tubes even after he developed his model. What he wanted to do was he wanted to get what was called the charge to mass ratio of the electron. So remember, ladies and gentlemen, from our previous unit, how Millikan here, he discovered the elementary charge. So I'll get this written down. Now, what's super cool about this is as Millikan was able to discover the elementary charge, well, guess what? If you can find the charge to mass ratio, then you can mathematically calculate the mass of an electron. So that's a pretty neat thing to be able to do. So what Thomson did is he would apply an external magnetic field to the cathode rays, and as they were traveling in a straight line, he would then notice how the cathode rays bent in a circular path. Does this sound familiar, guys? Yep. Back to forces and fields, unit 2. And then what he did is he'd measure the radius of curvature. Well, why is that handy? Well, remember, ladies and gentlemen, back from unit 2, that FC is going to equal our FM. Okay, so we're going to take our centripetal force and equate that to our magnetic force, and we can then mathematically solve for the charge to mass ratio that Thomson was looking for. So our MAC, as we know, is equal to QV B perpendicular, and mv squared over r is going to equal qv b perpendicular. Is this looking familiar at all? I certainly hope so. So we can cancel out those v's there, being the same value on each side. So mv over r is equal to qb perpendicular. And go back up and move up here, so I've got some space. There we go. Well, the thing is that we want the charge to mass ratio. So if we want a charge to mass, what we don't want just Q, and we don't want just M, we want Q over M. Okay, so we need to rearrange this so we get Q over M. So I'm going to divide both sides here by mass, and then I'm going to divide both sides by B. Okay, so once you have done that, you are going to wind up with your Q over M is equal to your V divided by B perpendicular times the radius. So this, ladies and gentlemen, this Q over M, this is your charge to mass ratio. Okay, so that is what we're looking for. Okay, that's what Thomson wanted to find. Okay, so this is still really early on in the studies of atomic physics here, and like this stuff was revolutionary. They're trying to figure out the bits that make up matter. I mean, it mattered. See what I did there? Yeah. So they didn't have the mass on the back of an electron on the back of a data sheet the way we do, and so they were trying to discover this, which is quite exciting. All right. So, ladies and gentlemen, let's do a calculation. The kind of thing that Thomson was going to do. Okay, or was going to, did. So, ladies and gentlemen, charged particles are traveling horizontally at a speed of 3.6 times 10 to the power of 6 meters per second when they enter a vertical magnetic field. Now, the key thing with these two, ladies and gentlemen, is to do what? Tell you that our magnetic field is perpendicular to the path, which is what we want. Okay, of our 0.710 Tesla, if the radius was deflected this much, so there we go, 9.5 centimeters. And what is the charge to mass ratio of the particles? So we want our Q over M. Okay, that's what we're trying to find. So just like we did above, if you are asked to calculate the charge to mass ratio, this is going to be your strategy. And just as we did above, our mv squared over r is going to equal our qvb perpendicular. Cancel out those. We wind up with mv over r is equal to qb perpendicular. And then we're going to divide both sides by m, so we can get q divided by m, and divide both sides by b to get b over onto this side. So we're going to wind up with q over m, so our charge to mass ratio. Take 3, ladies and gentlemen. Sorry guys, Screencastify kicked me out again. So we're going to continue from where we left off with this calculation. So where we left off is we had just derived our Q over M is equal to our V divided by our R B perpendicular. So that's where we left off. And now we're going to plonk in the numbers that we've already written down on the previous section of the video before Screencastify kicked me off into our equation to get our charge to mass ratio. So the speed of our particles, ladies and gentlemen, is 3.6 times 10 to the power of 6 meters per second. And then we have our magnetic field and our radius. So our radius is our 9.5 times 10 to the power of negative 2 meters and 0.171, excuse me, Tesla. Okay, so our charge to mass ratio, ladies and gentlemen, once you've plunked that into your calculator and put that into appropriate significant digits with units, is going to be 5.34 times 10 to the power of 7 coulombs per kilogram. Okay, so ladies and gentlemen, how do we know that this is going to be our units? That's a challenge. I want you guys to take some time, and I want you guys to try doing some unit analysis to figure out those units and why they make sense. Okay, I know we've done it a bunch, but I want you to give that a shot. Okay, so ladies and gentlemen, on to our next piece, next calculation of the day. So what is the speed? So we've been asked to calculate V of an electron that passes through an electric field. Here's our electric field strength of 6.3 times 10 to the power of 3 newtons per coulomb, and a magnetic field. Okay, so of 7.11 times 10 to the power of negative 3 Tesla, undeflected, ladies and gentlemen. Okay, assume that the fields are perpendicular to each other, which is what we want. So undeflected, ladies and gentlemen, what does that mean we do? Think back to second unit. What do we do? What do we do? What do we do? No, we don't panic. Make an F-net equation. So with your F-net, okay, so remember, it's 0 because of the word undeflected. Because of that, we have our FC. Beg pardon, that should be an FE. Where's my eraser? There we go. FE is equal to FM. Okay, so ladies and gentlemen, remember from our previous unit, our FE is equal to Q times E times Q V B perpendicular. Okay, the Q's cancel. Okay, and we're trying to find the speed, so I will divide both sides by B perpendicular. Okay, so ladies and gentlemen, we take our values, E divided by B perpendicular, 6.3 times 10 to the power of 3 newtons per coulomb. Divide that by 0.7. Now, let's write this properly here. It's Monday. It's not really. Really, for me, it's Friday today, but that's okay. We'll blame everything on Monday, no matter what day it is. Okay, that's better. Plonk that into your calculator, and we wind up with sig digs in units of 8.86 times 10 to the 5 meters per second. So another thing I want you guys to do is I want you to also do the unit analysis for this. Okay, I want you to give that a shot and see why this works out to this. Okay, why Newton divided by coulombs, or newtons per coulomb divided by Tesla is going to give you meters per second. Okay, challenge accepted. Cool. All right, so on to our next piece, ladies and gentlemen. Practice problems. All right, so pause the video for a few minutes and then do a practice problem or two, see how you do. And then we'll start looking at Rutherford's work. And we're back. I didn't actually stop filming in case you haven't noticed. No choppiness like the other 2 times the computer booted me off. 3 cheers for technology, yeah. Okay, ladies and gentlemen, on to our next piece. So we are now looking at Rutherford. So Rutherford was the next scientist to move the structure, the idea of the structure of the atom forward. And so what he did is he took a bunch of alpha particles. Now remember, alpha particles, they are 2 protons, they are 2 neutrons, and as we'll be looking at later, a good source of them is some radioactive elements. Okay, so what he did is he got a source of alpha particles, which what it is irrelevant, most likely a beam of radioactive stuff. Okay, and so he's got this alpha particle beam, and he's got a fluorescent screen around it. And what he did is he took this thin gold foil and fired a beam of alpha particles through it. Now, this part you've already probably remember hearing back in Science 10. And most of them scooted right through as he expected. So this big red beam is the undeflected alpha particles. This is what was expected. Okay? That's what he expected to see. However, what he did not expect was to see these deflected alpha particles. You see these thin lines? These alpha particles are being scattered all over the place. That was not expected at all. And some of them even came right back along their original path, like back that way, like back this way. It was insane. So he was shocked about this. And what he was expecting was like shooting bullets at tissue paper and then having them bounce right back at you. I love that reference. So completely unexpected. Okay. So what he deduced, based off his observations, what he concluded is that the mass of the atom is not evenly distributed like he expected. Okay. Or what Thomson had expected with his raisin bun model. Okay. However, he determined that the bulk of the mass, so the positive part of the atom, was concentrated in a very small region of the atom called the nucleus. Okay. And for center. Okay. Like the nucleus of a cell, nucleus of the atom. Yeah. So the bulk of an atom, the bulk volume, it consists of the electrons. Well, as Thomson had learned from this charge to mass ratio and combined that with Millikan's stuff, well, the mass isn't much. It's tiny mass. So, which explained why most of the alpha particles went straight through like this. This is what was expected. They would all punch through the atom. But here, they're going through, but deflected sharply when they came close to the nucleus. So because most of the volume of an atom is nothing, just empty space. Because electrons are so tiny and nuclei are so dense. Okay? So the more massive but small volume center would only cause some of the alpha particles to be deflected. Now remember, alpha particles are positively charged. So when you have an alpha particle come close to the positively charged nucleus, they're going to repel each other. So that's other evidence to why the deflection was in the pattern that it was in. Now, there's a big flaw in Rutherford's model, ladies and gentlemen. The big flaw is that if a positive nucleus is going to be concentrated around the center of an atom, what's going to keep the electrons from being pulled into the nucleus via electrostatic attraction? So that was an issue. Okay, so what they came up with to kind of help with this is the planetary model, where the atom would be like electrons are going to be orbiting the nucleus, like planets around the sun, and the electrons would stay in orbit. Now, the big problem with this, and which you guys, I hope you remember from our last unit, is that when you have accelerating charged particles, you get EMR. Think back to our previous unit. When EMR is emitted, the energy of the particles going to go down. Okay? Think back to the photoelectric effect. It's the big piece of that one. So with the problem here, ladies and gentlemen, is if the electron is going to be emitting energy in the form of EMR, its electricity or its energy is going to go lower. And as it loses energy, it's going to start losing momentum. It's going to start spiraling towards the nucleus. It's going to lose its kinetic energy. That's a problem. So that would mean the atom would collapse almost like instantly. And since we know atoms are pretty stable, I'm fairly certain atoms aren't just randomly collapsing, that this isn't going to be the exact model. Okay, so here's your nucleus. And if you have an electron that is orbiting, well, it's accelerating, because remember, the definition of accelerating can mean a change in direction. It doesn't have to be speeding up. And if we're orbiting, you're accelerating. Okay? So as this electron is curving like this, well, it would beam off a photon. Okay, well, then it would have less energy and would spiral closer, but it's still curving. So then it would beam off another photon. Okay, well, then as this process continues, it loses its kinetic energy, and then we have an electron colliding with a proton. And atoms don't work like that. So that is the big source of error in Rutherford's model. Okay, so what would end up happening is we would need another model to finish the explanation of this. And that, ladies and gentlemen, is the tale for another day. We shall like a good mystery novel. We're going to leave you in suspense at the end of this chapter, and then we'll start discussing some more properties of atoms later. All right, so later, alligator, and here are some practice problems in your workbooks. Gave those a shot, and I've also got some more practice problems here for you guys. Give some of those a try. The answers are underneath. Okay, so give those a shot. And no fires, injuries, or explosions. We will talk to you all later. If I can turn this off. Stop button. We got it. Bye, guys.